Hi guys, can you guys hear me? I don't know what to do today. I just thought I'll stream for some time. I'll surely solve some problems, but not right away. Bam, 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 bam. So guys, give me some options to do. Like, what can I do? Do you guys have any problems? Is there anything that's happening recently, like some contest or something like that has happened recently? Thank you, bro. I see you first in YouTube and subscriber to in last 2 months, but you're too advanced for me. I'm nothing to see be a kid I am. Someone has texted me that. I mean like in my oh should I try IICPC? I need 10 viewers at least. Also like guys. 10 viewers or 10 likes. You have 17 viewers, damn. Like the video guys. We need 10 likes or 10 viewers, whatever. I was trying to wash my face and face wash went into my eye. I'm sharing my screen because we have like 17 viewers. I mean, I don't prefer lead code too much. Okay, maybe I'll try IICBC. Hi, Tom Scott. I remember you a bit. It was long back. Yeah, you were supporting me. Yeah, you were supporting me a bit. I just remember that. In my last stream, you were there. A deer was staring at you in IDM. Nice. So someone has sent me this one. What is this? But I like the way you solve. First, I don't understand you. Your advanced thinking. What is my advanced thinking? But I watch live because I'm fan of your problem solving. Because he just want to see my from last 2 months. I never thought you reply. Damn. What is he thinking? But just try to ask what is the way to learn DSA. You reply, thanks. We'll check again. Clearly your channel's live section. Okay, if you leave that, what should we do? Should we try IICPC? Have you felt a shift in the problem pattern on CF? Lost due to was an exception. The problems seem to be getting more and more ad hoc. It's either an IQ test or guess forces. I don't know. I like to believe like we have same ways to solve the problems. Like we have. I would like to believe like I would like to keep it simple. Okay. Okay. Maybe then I'll try out Mirror when it is released. I'll try out Mirror. Now what should we do? Someone asked us some bi-weekly hard. Just a stream by just a boy. Yeah, who calls himself smart. So someone asked us something. Lead code fourth problem bi-weekly and weekly. I'll just try that quickly. Thought you were too good for me, my dear. Never gave me time of day, my dear. I keep fucking my privacy on here. Feb 2. It is Feb 2 already. Time passes very quickly, guys. Like it's 1/12 of 2026 has been passed. Should we discuss about Epstein files or like see, I was always pro. I should not say these things. They'll ban my channel, I guess, right? Not ban, but yeah, my channel is small, so they wouldn't care anything. But yeah, I was always pro Germany and against Jews. Mm. Have you felt a shift? I wish I knew you wanted me. Who is Gracil? Okay, I know. I have heard the name before. Where do you live in Bangalore? I have to move. I have to move. I bite my tongue, it's a bad habit. Kinda mad that I didn't give a kinda mad that I didn't take a stand, but I thought you were doing good for me, my dear. So when was it? When was the weekly and when was the bi-weekly? Feb 14 they had a, had a bi-weekly contest. Two cubes. So weekly contests were like that. They wantedly kept two cubes, I guess. Oh, it's because of bi. It's because of weekly there is only one. Mm, so what was the recent contest? We're not past contest, guys. I'm not very much aware of this interface. Jan 31. So this too, right? Okay, maybe I'll try this weekly. Can you also do lead code problem of the day? I'll try lead code, but give me better. Give me better problems. I'll try to do it quick. I won't explain well because I want to do more things. You're given an integer array nums. A subarray is alternating if one of the following holds. If the first one is less than the next one, which is greater than the next one, which is less than the next one, which is greater than the next one, and so on. And okay, if one of these holds, either it should be like this, like this, like this, or like this, like this, like this. Then we call it alternating, it seems. Okay, in other words, if you compare adjacent elements in the subarray, then the comparisons alternate between strictly greater and strictly smaller. So if you see adjacent elements, like it's strictly greater than the adjacent ones, or it is strictly less than the adjacent ones. You can remove at most one element from nums, then you select an alternating subarray from nums. Return an integer denoting the maximum length of the see, these problems are not good. They are like more of brute force problems. But if you take code forces, you'll have nice problems. So don't get confused with lead code hard because there can be shitty problems in here, right? It is a bit brute force because removing something and then trying to check for the maximum length subarray is brute force, right? Like it involves some brute force at least, right? So uh, you're removing something. You can remove something at most. It's your wish. You can or you need not. I will not solve this one. I will not solve this one. But I think if you can find, if you can find from this at some point, if you can find this alternating sequence that ends this side. I mean, if you can find the longest alternating sequence that is starting from here, we have two types, which is less starting from less one, starting from greater than. So if you have that longest alternating sequence starting from here, if you have that alternating sequence starting from here, I mean, if you can find such a thing starting from here, what is the longest alternating sequence length, then the problem is done. How? You can brute force on what you're removing. Okay, if you're removing this, you will brute force on that. And then how will you do it? If you're removing this, you will try to check if you can connect this and this. And from here, alternating longest, and from here, this are alternating longest. This side or this side is or same problems, right? I'm not explaining it well, I guess, but what I mean is this is alternating symbols, right? Like if you can just solve starting from here, what is the longest length? Which is same problem as starting from ending at here, what is the longest length, like this side. Both are same problems, right? I have been outside a bit, bro. I haven't been in my place, and also have been busy. That's why I haven't had any. I didn't get time. Even today I was not liking to, but so guys, if you can have this thing, like you want something like alternating thing, it seems, okay. uh If you can find starting from here, what is the longest length? And we have two types of things. Okay, type 1 and type 2 will have longest lengths, which is same as ending at here, what is the longest length? And then there is something in between. There is something in between. Maybe you will skip that and then you will see if you can connect these two things. In that way, you can get the longest alternating subarray. It's like brute force. We can go, but I don't think we have that much time. So this problem is not that good. Like it has nothing in it. Like it should just, it's like brute force. So now we have to think, how do you find longest alternating subsequence? Longest alternating subsequence length. How do you find that? It's not difficult, right? You have two types of starting with less than symbol, starting with greater than symbol. So for this, to find starting with less than symbol longest, either this one, or if you can connect these two starting with the opposite symbol longest. So it's like a small dp. Like how do you write starting with longest, starting with less than symbol longest from L? If you can connect these two things, which is if L is less than L plus 1, then starting with here, what is the starting with greater, what is the longest starting from here? So it's not difficult to write the dp, right? So guys, hard problems are nothing. See, you guys are just lazy, or you guys don't try hard enough. Like this is not even a difficult. This doesn't even has any good logic in it. It's like same type of brute forcing DP. Brute force and DP are the same things, right? This is it, right? This is okay. This is weekly. I'll go for bi-weekly then. It's not even casework. I mean, it's a shitty. See, these problems are bad problems. This will give you in code forces and at difficult levels. We may have nice problems, which are difficult but they are nice. So what rating should I solve, guys? We have viewers, but no, none of you guys are liking the video. Hi Ari, I have seen that you have gotten sixth rank in ICPC regionals. That's nice, bro. Sixth rank is nice because you have many big colleges, right? We need 20 likes, guys. Like we have viewers, but okay, bro. Shout out to Utkash Anand for getting seventh rank in which your college, but not you. Niga, when will you get a good rank? My college which Pilani got is what you are telling. That's fine, yeah. Okay, I will once see bi-weekly fourth one. I will read it, I will judge it, and then I will move on to some code forces problem. I will not solve them. I will solve at least few problems for sure, but uh, I will not solve some time-taking, not good problems because this is a time-taking, not good problem, right? Right. I mean, I can code it quick, but it's still time-taking. So they have a contest for coders on Feb 14. I will read the problem, okay? Uh, I may have some new viewers, right? For that reason, I'll try to solve this problem. Okay, just for some new viewers, I think we may have right, like some new starting beginning viewers. You're given a string S consisting of lowercase English letters and special characters. Your task is to perform these in order. So we have a string that has ABCDs in it, which are also small, not big letters. Your task is to perform this in order. We have to do these things in order. In order is in bold here. Reverse is also in bold. Reverse the lowercase letters and place them back into the positions originally occupied by letters. We have to reverse the lowercase letters. Okay, we have special characters too. That's scary. We have to reverse the lowercase letters and place them back in the original position. Reverse the special characters and place them back into the positions originally occupied by special characters. So how does that happen? Like, okay, okay. Wait a minute. Return the string after performing the reversals. So first we have to do reverse the lowercase letters and place them back into their originally occupied by letters. So we don't touch the other things, and then what do? We reverse these things and then we place them. So this becomes that, and then so this seems we understood, like first we have to just see the letters, ignore all the characters, see the positions and then reverse them, and then we have to see just the special characters and then we have to reverse them, right? How do we do? Should we separate them and then should we reverse them and then again should we place them back? Maybe I'll just do that. Okay, strings or vector char I will use. Vector is just a list. Okay, uh lowercase special. Okay, now we are going over each character in the string, and then if okay, I will make a function. We can use functions in coding for new viewers. Functions are nothing but I want to explain programming, like I want to make a new video. Functions is nothing but if you want to use a piece of code again and again, you can write it as a function. Is lower that takes a character and its work is to say if it is between a and z. Okay, if it is a lowercase letter or not. So you can have this piece of code somewhere and then you can use it again and again. So that's the use of functions. Like this is a function that does something, you need not care what it does inside, but you can only know what it returns. If it is lower, push into lowercase. So this is we are iterating over characters. This is we are trying to push it into this shit. So now what I will do is I will define string answer and then I will try to go over again cats. Okay. Now if it is lower, what will I do is I will remove the last character of this and then I will push that into S. Okay. How to push the last character? To get the last character of a vector, you can do dot back off. Okay. So I'm pushing into answer. Answer dot push back off. What am I pushing? I'm pushing lowercase dot back off. Okay. And then I will remove that. I mean, this is unnecessary usage of vectors. We can do it more simpler way, but I don't know. I'm just trying to do this. Now it is special character. See, we are reversing it. How are we reversing it? Because I'm pushing it, because I am popping it from back, we are reversing it. It's not difficult to understand this, I guess. It might be a bit difficult if you're new to coding, but this will be the answer. You can just return it now. So see what have happened. It is actually reversed. F A D C B E. You can submit it. You have it accepted. So how was the explanation, guys? Yo, how are you doing from Vedant Pandey? I'm doing good, bro. How are you doing? Please do four. How was one, guys? Who's newbie? Yeah, long time no see. Is it lagging still? Taya smartness day by day. What do you mean by smartness? Like, is it how I look or is it how I think or like, is it what does smartness mean? Night dawn. I think I have done that problem, subsequence addition. Is it in recent one? We'll solve some nice code forces problems. What do you mean by please give my blessings? Maybe watch my videos, maybe share it. Like I'll be happy that you have done that. So guys, we are at fourth problem now. Okay, bi-weekly fourth problem, right? You guys wanted minimum partition score. You're given an integer array nums and an integer k. Your task is to partition nums into exactly k subarrays and return an integer denoting the max minimum possible score among all valid partitions. So we have to partition. Partition means split it into k subarrays and return an integer denoting the minimum possible score among all valid partitions. So what is score? Score of a partition is the sum of the values of all its subarrays. Okay, what is value of a subarray? It's defined as sum ARR times sum ARR plus 1 by 2, where sum ARR is sum of its elements. So what do we need? You have this sum. So what the problem is you will split the array into k parts. Okay. Let's say after splitting the, I mean, these are all bad problems, guys. These are not good problems. These are all brute force problems. See, nums is 1,000. It's a brute force problem. Value is also 10 power 4. You have one summation here. You have one summation here. You have one summation here. I hope these are nice problems, but they are not. They are mostly brute force problems. You want s1 times s1 plus 1 by 2 plus s2 times, let's say s1 is the sum before this partition, before this boundary, s2 plus 1 by 2. You want to minimize this thing, it seems. Minimize this. I'm not doing this problem. Okay, I'll try to think for some time, but so k is fixed. So how many partitions you split? You have to fix that too, and you have to count this one, right? Mm. So can you do it like, can you use DP like for all number of partitions and all? Let's say you're fixing S5, this length, and then you have this one now. It is k minus 1, splitting the remaining things into k minus 1. What is the minimum sum if you can have that? Right. So, so if you have for this splitting this into k minus 1 thing, see, these are total k groups, right? So we are trying to brute force, let's say. We are trying to find the problem. We are trying to somehow brute force the problem, solve some simpler problems, smaller problems, not simpler problems. So let's say you're fixing this side, this S5, the last group. Okay. And then you have to split the remaining things into k minus 1 things, right? You have to split the remaining things into k minus 1 things. And then let's say dp, not dp, like answer of n of k means if you look at n characters, and then let answer of I of k, let's say. Okay, answer of I of k is 0 to I, split that into k characters, k groups. uh, what's minimum score? Okay, this is that, let's say. Now let's say you're fixing j, and I to j, let's say this is the last group. Okay, if this is the last group, if that is the last group, you have its sum as s into s plus 1 by 2 plus answer of j, because from here you have to split k minus 1 groups, right? K minus 1. So it seems to be possible. I mean, not possible, but religion all designed to keep you safe. Start doing. I don't know like how to solve this. Like if you reduce j, this will also become smaller, and if you reduce j, like this will also become bigger. Can we find where it will become optimal? In n cube, I can do this problem, but n square, I don't know. I don't like this problem. Let's leave this problem. Okay, we'll solve some other problem. He can try. Binary lifting is not that difficult. Okay, no deep four. I don't like deep four. It's a convex fix. I thought so. I thought so because one goes like this, the other comes like this, or something like that, so we can find the optimal. I thought so, but then it's a stupid problem still, right? What does my smartness mean, Smackdown? I have my roommate. He's saying something. Oh, would divide and conquer work? Divide and conquer can be a good thing. Guys, don't give me those terms. Like it hurts me. Don't give me like DP optimization. Divide and conquer is a nice one. So guys, this is also not that good problem. In n cube, I can do this. How do we do it in n square? I mean, it has nothing. If you're using some technique to find what is the optimal thing, I don't think it's that great, right? Or all the numbers positive? Yeah, all the numbers are positive. Maybe we can find optimal in some way. Maybe you can do binary search and then go to some optimal point. But how do you prove that? How do you prove that this is a convex function or something like that? How do you prove that this is an convex? I can say this keep decreasing, this keeps increasing. So this one keep decreasing, this one keeps increasing, and one is decreasing, the other is increasing. Uh, but that doesn't give you. One is decreasing, the other one is increasing, so likely it is like some convex function or something like that. Then you can have you can use binary search to come to the middle point, but it's not easy to prove that, and it's a shitty problem even if it is true. Bro, wallet day by day. That seems like a good thing to do. That seems like a good thing to do. So I haven't given some virtual, so I'll give one virtual now. I haven't given this division 1 division 2 itself. Should I try division 1? Should I try this division 3? Say guys, I will try one to 2600, I guess. But do I have energy for that? As my goal is international grandmaster, I will try problems in this rating, okay? This one seemed like a nice problem last time. Last time. But it can be much more difficult. I'm not spending my energy anywhere. Macdown recommending something according to my smartness. Finally. Don't take membership, Mikoyan. Mikoyan is the only one who took my membership. I can try here. This is 28. 28 is not difficult, guys. I have done long back. I have done long back problems in these ratings. Have I done any problems long back? See here I have done few. And if you go down, I might have done more. In 2023, I was doing more. Now it's 2026. 3 years have passed. I remember this still. See here I was doing it. Right. I achieved uncle. Someone called me uncle recently. Some girl I was talking to called me uncle. UNC. She's young too. That's why I guess. Mm-mm-mm. Okay, I'll go for Div 3 virtual because I want to keep this stream light. I don't want to try difficult ones in here. Tomorrow I may get my drawing pad, then I will try difficult ones, okay? Damn cooked. Skincare I have to do, bro. Not jerking off is the way, okay? Hi Yash Mohta. Not jerking off, working out a bit. That's the way. I don't have much muscles, but yeah. And you should get wings too. What do you mean voice gone? I'll skip, bro. I'll skip them. I'll try Div 3 virtual. No, not this time. We fucked up. I don't mind, but yeah. hmm So it starts in 4 minutes. Should I write these problems? Divisible permutation. You're given an integer and construct a permutation p of length and satisfying the following condition. Adjacent things should be divisible by I. For n, it's always divisible. For it's divisible by I. That seems scary, right? Like at the end, n minus 1 should be divisible by the last thing should be divisible by n minus 1. So it should be n and then it should be 1. After that, I think it is coming like this. But that's a difficult problem, right? I think but it's a difficult problem. It's like coming like this, like this, like this, like this. So I think there is a way where you will make p minus pi plus 1 equals to plus or minus I. It should be divisible, but there is a way in which you can make them plus or minus I. And the way is this. Uh, so the problem is looking like you have to make it divisible, but how do you make it simpler? Just remove divisibility and guess maybe it is plus or minus I. Uh, pi minus pi plus 1 is divisible by I. We can guess pi minus pi plus 1 equals to plus or minus I. I think this exists. This exists. You place n here and then you place 1 here. Okay. And then you place n minus 1. And then you place 2. So what is happening? N minus 1 is the difference. N minus 2 is the difference. N minus 3 is the difference. So if you do that, I think it works out. Start equals to 1, end equals to n, let's say. Come from behind. Okay. Alternate. You have to alternate to. I will choose some constant to alternate. Okay. I equals to n minus 1, I greater than or equals to 0, I minus minus. Okay, if c is even, if c is 0, then what will I do? I will keep end. So what does c will become 0 1 0 1 0 1 because I have to keep n ending starting, right? So s will have starting number, e will have ending number, c will alternate. So if c is 0, like initially it is 0, we have to keep the ending one, and then I'm reducing ending by minus 1. Else we have to keep starting one, and then we have to increase starting, and then we have to alternate c. This is like alternating, it flips from 0 to 1. Now we will output it. This should be working. But it's not a easy problem, I guess. It's not an easy problem. The fact that it's guessable, I think it guessable makes it easy. But what is triple IT says contest? I don't know that. So are we on time? See how we have simplified divisible by to plus or minus I. So they will unnecessarily make it a bit complex. If they have told this, maybe you would have solved easily, right? Start from I equals to n minus 1 because divisible by n minus 1 is difficult, right? Why is it difficult? It's either n minus 1 or 2 times n minus 1, but 2 times n minus 1 is not possible. So it gives off it should start with n and 1 or 1 and n. Any of them will work. We'll try h first. I don't know how difficult is it, but we'll try this. The great Grail tree has stood in the kingdom for 315 years. It takes up a lot of space. So King Leah decided to get rid of it as soon as possible. The tree itself is an acyclic connected undirected graph. Acyclic means it doesn't have any cycles. Connected undirected. It's just a tree. Okay. The tree itself is an with n vertices each having its own value AV. The tree can be removed in the following way. Let SV be the sum of the values of all remaining neighbors of V. So see, these are nice problems, right? Compared to the shitty problem we have seen here. So this has something to think. I don't know. Maybe this is also a shitty problem because we cannot expect more from this so easily. Let's read the problem, then let's judge it after reading it. Let SV be the sum of the values of all remaining neighbors of V. So SV be the sum of all remaining neighbors of V. If V has no remaining neighbors, then SV is 0. Choose a vertex V such that AV and SV differ in parity. Oh, seems a nice problem. So AV and SV should differ in parity. We have to choose such a uh, vertex. That means if AV is even, SV should be odd on, or if AV is odd, SV should be even. If there are no such vertices, stop the process. Remove the vertex V and all edges connected to it from the tree. So we can remove some vertices. And the condition is sum of the parity of the remaining vertex values should be different from this parity. Okay. Your task is to determine whether there exists a sequence of removals that will lead to a complete removal of the Grail tree. If such a sequence exists, output the sequence. It's a good problem. It's definitely a good problem, guys, because if there is a way to remove everything, you have to output the sequence. It seems if there is no way, you have to report that. So it's a good problem. You can think when it is possible, when it is impossible. If there are multiple answers, you can output any of them. See, it's a nice problem, right? So the fact that you have to also output the order makes it an easy problem, but it's a good problem still. So why don't you guys try such difficult problems instead of trying this stupid difficult problems? These are stupid not because of the logic. These are difficult not because of the logic. These are difficult because they have multiple stupid steps. But this is a good problem. Do you guys agree that it's a good problem? Say values doesn't matter. All it matters is 0 or 1. So let's say these values doesn't matter anyway, because uh, even in the summation, value will not affect. So we have some zeros, some ones. Okay, we have some zeros, some ones. You can remove one vertex if its parity doesn't match with some of the remaining parities. Okay, can you remove everything? And if you can remove everything, what is the sequence? Maybe you can try something a bit. A single zero cannot be removed, right? A single zero cannot be removed. That's an initial thing you can easily say. Let's say you have a single node whose value is 0. Values are either 0 or 1, okay? Doesn't have anything. Because it doesn't have anything, SV is 0. Because if there is nothing, SV is 0. They have told us that. So if there is a single vertex, okay, its value must be 1. Its value must be 1 for single vertex. Okay? So finally, a single vertex will be there, right? If you're removing one by one, there will be finally one single vertex. Maybe there will be more single vertices. Zero can never be a single vertex. Okay, so if zero is a single vertex, you cannot do this. I haven't logged. I just closed the door a bit. He logged his roommate. 6132. What is the significance of 6132? So one has AV equals to 1, SV equals to 0, then you can remove that. That's just the first statement you can make. You can say that. Why is my laptop slow? I bought it like some very high model because my company is paying for that. But if there is a single vertex left, it must have AV equals to 1. Value doesn't matter. Only its parity matters. So all values are either 0 or 1. Okay. Is it possible to remove? I'm thinking something. So if there is a leaf, if there is a leaf with 1 and 0, let's say this is 1 and that is 0, then you can remove that. If this is 0 and this is 1, then also you can remove that. Like if there is a leaf where these two things change, you can remove that. Right. We have to see the problem well. What does it mean that this and the surrounding things should be different? It's nothing but it's nothing but there is something different. There is something different. So if you see, problems are always about seeing the problem for what it is, okay? Rather than going to test cases and all, you have to see the problem for what it is. What it is exactly. It is nothing but there is something different in its adjacent list. This is what it is. See, guys, you have to see the problem for what it is. Like, you have to see it well. So, what does that mean? If AV and some of the other things are different, what does that mean? So, if this is one or no, or odd number of things are there. Okay, if this is zero, if this is one, no, sorry, I haven't seen it properly because some right, some some says something. Okay, if this is zero, then there is a one. If this is zero, then there should be odd number of ones to be removed. So let's try something a bit more. If one is a leaf, if one is a leaf, you can either remove this or you will remove this, right? Whenever you remove an edge, you will either remove this one and then the edge will be gone, or you will remove this one. Like let's say this is leaf and this is the tree. You have this tree here. This may have more things too. Is it beneficial to remove it right now, or removing this might be better? So if this is zero, you must remove that. That you can say, because if there is zero, okay, where did I write that? Okay, if there is a single vertex left, it must have AV equals to 1. This we have gotten, right? Because if AV equals to 0, also SV equals to 0, and it's impossible. So what you can first do is you can remove all, you must remove. So you must, this will also immediately give that you must remove all leaves with values 0 before their partner. Because if you remove this partner first, then this will become single and you can never remove that. So this thing you should be able to remove. And when you're removing this, if this was 0, then it's impossible, it's again done. So when you remove this, this must be 1. Okay. So now you removed all leaves with value 0. Now you have leaves, all leaves with value 1. Okay. Now we have leaves with value 1. And now we have leaves with value 1, right? Now what can you say about leaf with value 1? What can you say about a leaf with value 1? 1 0. These are the same things I was trying to look here. Okay. Leaf with value 1. If this is 0, you can remove right now. Right. But how would you remove that? You can remove it just like this. If this is 1, you cannot remove this because 1 and 1 are connected, right? You can never remove this if it is 1. You can only remove this if this is being removed. Otherwise you cannot remove this edge by removing this one. You cannot erase this edge by removing this one. See, we will try to remove this or this first, right? First you cannot remove this because this is 1. You have to remove this first. So in these cases it's known that you must remove this before this. Now let's think about that one. What is going first before something else? Think about that. Think about that one. Let's say, I think I have done this before long back. Uh, you care about what left first. Okay. This makes the tree directed. What do I mean by that? Let's say you have your tree. Okay. So if this one left first, we will keep it like that. If this one left first, sorry, if this one left first, we will keep it. Oh, okay. Uh, if this one left first, we will keep an arrow from here to there. Okay. Okay. So in the order they leave, so first this one left, and then this one left, and then these two left, or something like that. So if you see, there is an ordering. There is an ordering in which, if you look at this one, the value in this and the value of all these things which are after that, which are living after that, all of them must form one value. Their value should be one. So that's what the problem is, right? You have viewers, it's very boring, right? Blitz stage. I'm not collecting this yet. Blitz stage is my old ICPC teammate. Maybe he's trying to support me. Uh, um, I don't know how to collect this thing. I mean, I can collect in future, I guess, but I have to collect that somehow. Where is revenue? I have to collect. Oh, total it is a bit, but I have to collect it slowly. mm Blitz stage is my teammate. So guys, we have to solve this problem for sure. Okay. Uh, so what should happen is all the leaves should be ones, and if a leaf is zero, you must remove it right now, because if a leaf is zero, you must remove it right now. So the condition is that after you make this ordering, so the problems are equivalent if you think about it. Is there an ordering of these things such that, is there an ordering of edges such that, uh, for every vertex, its outgoing edges its outgoing vertices, and that vertex should be 1. Their value should be 1. This is the problem very clearly. If it is a leaf, if it's a leaf, its outgoing vertex should, if it's a leaf and it is 0, its outgoing thing should be nothing, or its outgoing thing should be 0. Wait a minute. If it's a leaf, it must be like this. If it is a leaf and 0, it must be like this, and this must be 1. Why? We have seen, right? Because otherwise, if a leaf is 0 and if it doesn't have any outgoing, so a vertex and its outgoing things should be equal to 1. That's the problem. If you can order all the edges in a way such that the vertex and its outgoing vertices will add up to 1, then the problem is done. Is there a necessary condition here? Think about that. A vertex and its outgoing ones, right? A vertex and its outgoing ones will be 1. A vertex and its outgoing ones will be 1. A vertex and its so the problem is equivalent to uh, a vertex and its can you order edges into directed? So ordering means, what is ordering means, this one will leave first and then these two will leave. So because if it's leaving first, you can see that when you are removing it, you can see that that and the remaining thing should be different, which is nothing but the total should be odd. Okay. A white component is definitely bad. A white component is bad. You can say that as a small observation if you want. A zero component is bad. If something is 0 and is entirely surrounded by 0, also this is bad. Why? Whatever happens, you can never remove that, right? We can say something like, if nothing is removable in the beginning, it's bad. It's possible sometimes nothing is removable in the beginning, but I should not waste too much time somehow. Like I'm wasting too much time unnecessarily, I guess. If I see the whole problem like this, is there a way in which you can direct edges, and then, and for each vertex, value of vertex plus outgoing vertices equals to 1. This is the problem. Is there an ordering such that the vertex plus the outgoing will be 1? So we have this necessary condition, right? Are there any other necessary conditions? This is a necessary condition. If something is 0 and entirely surrounded by 1 by zeros, it is bad. If there is a 1 and it has even number of, odd number of ones, I think zeros are the trouble. If you have only ones, let's say if you have only ones, you can always, no, you cannot remove, Leaf. If it is 1, you cannot remove leaf. If you have only, so let's look at this graph. You have one and then you have two other ones. This is impossible, right? Because you cannot remove this, you cannot remove this, you cannot remove anything. Okay, okay, sorry, three ones. Let's say you have this graph. This is one and the sum is one, and for everything it's one. So even these are bad. So when it is possible and when it is impossible, is it more easier than what am I thinking? Uh yeah. Can we do this? We have to solve this problem, guys, for sure. For sure. If both the values are zero, okay, this thing doesn't matter. This thing's direction doesn't matter, right? Why? Even if this direction is like this or if this direction is like this, it doesn't affect at all, right? If both of them are zero, that doesn't affect, like the direction doesn't affect at all. Why? Because whatever you do, it is not affecting the other thing. Okay. So one thing we found out was you can remove all zero leaves. That is first thing you found out. Can you proceed further when you have all leaves are ones? Can you proceed further? When all leaves are ones, okay. When all leaves are ones, if the shit is one, you must keep it like that because if it is like this, it's impossible. Okay. When all leaves are ones, uh, let's call something a leaf if only one it has only one edge that is not directed yet, okay, because we have found that all zeros we must direct them like this, because if you direct them like this, oh, if we must direct them like this. No, no, you must direct them like this. Why? Because they cannot have any outgoing. Yeah, they don't have any outgoing, so the outgoing, all zeros must be directed like this, okay, because uh, 0 plus, and this must be 1. So we can direct all zeros. So now leaf is nothing but it has only one non-directed one. That's a leaf. Let's give that definition to a leaf and let's see if we can proceed further and further and further. Okay. Uh, so I'm thinking because the problem has some structures which are always impossible, and the structures can be as shitty as like if everything is one, you have to see if there is an odd one or not, else it's impossible. If all of the ones are having odd degrees, then it's impossible. So they have such shitty things. So I think the structure is likely you can go progressively, like maybe you can remove leaves and then you can remove leaves and so on, rather than something else. Mm-mm-mm. Okay, if it is one and one, this must be like this, because if it is like this, it's impossible again, right? And this is a leaf is what I mean, no? So this is a leaf. This is a leaf. Okay, this is a leaf and this is 0. Let's leave that. Whatever is here, we have taken care of that already, let's say. Okay. Whatever these edges are, they have been taken care. All of them are directed. You can know one's effect there. Okay. After knowing one's outgoing effect, okay, after knowing one's outgoing effect, okay, instead of generalizing, let's not generalize first. Let's just look at one leaf and one, and then there is only leaf and this is one. Because when it is zero, we are able to progress. When it is one, if this is zero, when this is one, and if this is one, we are able to progress. We are able to say that the direction should be like this. Okay, the direction should be like this, because if the direction is like this plus outgoing will become zero, right? That's wrong. Now think of it. The direction can be like this, it can be like that. I'm not telling it should be like that, it can be like that, because then it's good. The direction can be like this also, even then it's good for this vertex. Why? If it is like this also, it's fine, because this is zero, right? So we have seen before too, if both are zeros, this direction doesn't matter at all. If this is 0 and this is 0 and this is 1, this direction doesn't matter to this, but this direction matters to this one. If both are ones, both directions will matter to both. Can we also say anything like, I don't know if I'm overcomplicating this problem. I might be overcomplicating. Maybe I got dumber. Yeah, my sheet is under my bed. No dark mode, bro. I'm sorry. Because in light mode, my face is more visible. I haven't gotten dumber. I'm distracted, that's it. Let's try, guys. Let's try this problem a bit more. Mm-mm-mm. Sum total of all observations, the sum of squares between. What is this? This seems like some sum of squares minus mean. SSB within sample sum of squares. Total sum of squares SST. Seems some statistics related one. Can we solve this shit? I'm feeling pressure, guys. It's been a while, right? I'm feeling pressure, unnecessary pressure. All zeros can be removed. I mean, it became more complex because I was trying to generalize. That's why it became more complex. Okay, if it is 1 and 0, it can be anything. That's the shitty thing, right? If it is 1 and 0, let's think about that. This doesn't affect. It can be anything. But till here this should be removable, and then this part has been done. At least this part has been done. Like, you need not worry about this part. Okay, but you have something like this can get help. And if this one's value is 1, then it can get help, and this can be removed. You need not worry about that. You need not worry about that means you can take this help finally, and you can satisfy this one. This can be removed. You need not worry about that at all. Is what happens to this vertex. This can always be removed. Okay, so what happens with all the ones, zero ones is, with all the zero ones, what happens is, whatever happens, this zero can be removed. If there is a zero one, this can be removed whatever happens. How? Because this thing doesn't affect one at all. What do you do finally? You can just flip this off, and then this can be removed. All the zero ones, all the zeros that are attached to one can be removed. So the problem is done then. Because if there is a zero that is attached to no ones, then we have seen, oh, this is all the necessary condition that we need. This is all the necessary condition. If you observe, the problem is always finding some finding some necessary conditions logically, and then the problem is done. And if all zeros have at least one, then you can remove them. Then you can surely remove that zero. But now we have ones. How do we remove ones? So these zeros can be removed for sure, because you have zero here, you have one here. Keeping this like this or like this doesn't help this one at all. But keeping this like this or like this can either save or break this zero. So using this one thing, you can affect it entirely. Whatever the other things are, you can save this up. So all zeros that have one can be saved. Likely, they can be saved finally. They can be removed. Like how? If there is a zero if there is a zero that cannot be saved, you will just flip this one. You will flip this, and then that zero can be saved. If there is a zero that cannot be saved, you can flip that, and then it can be saved. So all the zeros are saved. Guys, all the zeros are saved. Now we are dealing with one and one edges. Now all we have to deal with is ones. And if you think about ones, for ones, zero doesn't affect it at all. Even if you keep the direction like this or you keep the direction like this, it will not affect at all. So it's about one's connected components now. It's about one's connected components. Do you guys see we are making progress? A bit of progress, logical progress. Do you guys see that if there is a 0 and 1, this 1 will help the 0 to get removed. Like the problem has been converted to a vertex and it's outgoing. The value of this shit should be 1. The problem has been connected to this, and this should happen for all the vertices. Okay. Oh, I took a screenshot by mistake. So, guys, where are we? Because this 0 will not help our problem. This is our problem. If you direct the edges for each vertex, this value on the vertices at the directed end should be 1. That's the problem. Okay. For this 0 doesn't help at all. So it's like a connected components of ones now. So if you have a connected components of ones, can you direct them all in such a way that now there are no zeros here, because zeros doesn't help at all. So now we have just ones. Can you direct them such a way that for everything the directed thing is like odd? So now you look at leaves. Okay, for leaves, All that matters is for leaves what happens. So guys, zeros can be removed for sure. Okay, uh, if a zero is with all surrounding zeros, there might be behind she. What are you guys talking about though? There might be he behind she. Mikoyan, like, what did you say? I was not able to understand you. Oops. Ah, the problem. This is the problem. Do you want the link? I have changed the problem a bit. The problem was removing vertices, but while you removing it, I directed the edges to show the removing. Okay. Okay, if there is a vertex leaf, it must be like this. Okay. Now you are only having ones. Now you are only having ones. And let's call something that is having only one edge. If this is having only one edge and this is one, based on number of ones here, you can either direct this like this or like this. So guys, for ones it is unique. If you are having a bunch of ones, you can come from down. Let's say you're having only a bunch of ones. Okay, let's say you're having only ones. So it's a simple problem. Like, it's like I was thinking a lot unnecessarily because of zeros. So you can come from below. Okay, you can come from below. If this is 1, you can direct it like this, because if you direct it like this, it's impossible. So after that, you are here. Now, based on number of ones in the outgoing, you either direct it like this or you direct it like this. You get that? Based on number of ones, because everything should have, so all of these are ones, right? So everything should have outgoing even number or odd number of outgoing edges. Everything should have odd number of, everything should have even number of outgoing edges. Then you will have even number of ones, and then it is opposite. Everything should have even number of outgoing edges. What does that mean? So you can order everything after when you come here. Based on number of outgoing edges here, you can order this above or below. So you can order everything, and then you will come here. Finally here you will check if one is having number of things or not. That will either make it valid or invalid. So if ones can be ordered like this, the problem is done, guys. If ones can be ordered, uh, so you can order from below, and then you will come here, and then you will check if one can, if this is satisfied or not. If this is satisfied, the problem is done. And then for all for all other zeros that are connected to a one, you can save them with just this one. You can keep everything arbitrarily, and then you can just save them using this. And for zero connected with all zeros, it's impossible anyway. So the problem is done. But I'm thinking of one thing. Okay, I'm thinking of only one thing. If all of them are having, if all of them are having even outward, this number of outward is even for everything. If number of outward is even and every edge is in only one thing, so I will write it down for you guys. So you have to hear very clearly. We want number of outgoing edges should be even for everything, for every vertex, and every edge is will belong to only one vertex, because if it is directed like this, this edge belongs to that. And total sum is even. Okay, total sum of, for everything it's even, like for everything its outgoing edges are even, for everything, for this out its outgoing edges are even, for this its outgoing edges are even, and all of them will add up to total. So if the total number n minus 1, not n minus 1, the number of ones in this connected component, if this is even, if n minus 1 is even, if n is odd, it's possible. If n is odd, it's possible. So here n is not odd. If n is even, it's impossible. If n is even, it's impossible. If n is odd, it's possible. Okay. Because you can always direct them if n is odd because it's a tree. So all the ones should be of, we have necessary conditions now. See, we can either finally check this one, but I'm able to figure out that value right now itself because it's very fixed, right? I can either I can mark them and then I can go and check, but I'm able to figure it out right now itself because it's fixed, right? Because it's very fixed, it's very constrained. So I was able to figure it out right now itself because if the size of this odd component is even, we are fucked. If it is odd, sorry, if it is 1 2 3 4, if it is even, then this is odd, so we are fucked. If it is odd, we are good. If it is odd, we are good. So what are our necessary conditions, guys? So this is necessary conditions. Always we get necessary conditions. Okay. And now in one components, if size is even, it's impossible. Why is it impossible? We have seen. Once you fix all these things, what will happen is finally this will fail. This will fail. Why will it fail? Because you have this condition, right? And you made everything even. So you can know what is this because of everything adds up to some even or anyway. So if one thing is left, you can know what it is if everything is satisfied. Okay. And that makes it impossible. If size is odd, it's possible. You can just come from leaves and set everything. What about zeros? You can set them arbitrarily, and then if some zero is failing, you will, if some zero is failing, you will find the one it is attached to, and you will flip this edge, and then this zero is satisfied. Were you guys able to understand this one? Were you guys able to understand the problem? 13 viewers, I can understand that. One of it is my friend, I guess. So, guys, were you able to understand this? We have solved it in a nice way. Like I even gave you this thing, this nice thing. This algorithm, if it is only once, it's simple because this should be like this. This should be like this, and then for this, you can what this should be. And then I was able to even say that for everything, number of outgoing edges should be even because the value is one. Number of outgoing edges should be all values are one, and this value is one. We want one, and the remaining things. So, did anyone got it? So, guys, so first I have simplified the removal of things into directions, and after directions, the problem has been converted. We see zeros doesn't matter. One will not, zero will not affect one. So what will affect one? Only one's component, and then we came to one's component. For one's component, if size is odd, we can remove that. If size is even, we cannot remove that. Guys, someone respond, please. That's why I'm not doing streams, okay? Because you guys think I'm going slow, and then you won't follow. And then once it is solved, you will be like, what has been done? See, the problem with DSS sheets is people can't realize if something is being useful to them or it's being not useful to them. Why have I never tried any DSS sheet? Because I know it's about just solving problems, improving my skills, right? Like we have to improve my skills. Maybe I have to accept some problems and then feel better. Something is better than nothing, I guess. Like there's nothing special like you have there's nothing special like some sheet will help you. Like if you solve some problems, you will become better. And if you solve them in a nice way, you will become more better. Like if you observe things a bit more nicely, if you try a bit more hard, you will be better than most people. It's as simple as that, I guess. So this implementation is can be simple, right? For each edge we direct the edges, and we can direct all the edges. Everything is satisfied. And once you direct all the edges, what will you do? Once you direct all the edges, there will be something for sure with everything going out. Always there will be like something like that. Why? If there is not, you can follow in that direction. You can follow in that direction. You can follow in that direction, and you will end up with something that is having everything out, because there are no cycles, right? In a tree there are no cycles, so there will be something for sure with everything outward. How do you prove that? Because you can keep going behind, you can keep going behind, you cannot go indefinitely, right? And you cannot come to something that is existing too, because that forms a cycle. So if you keep going behind, if you keep going behind, there will be something that doesn't have any behind. You first remove that and you keep following the procedure. So in this way you can get the ordering, final ordering. So you direct edges in the black in the one components, you direct edges. For zeros you direct edges finally. Uh, and then finally, after directing all the edges, so Vamsi, do you got the solution? Like we have solved a nice problem. I have seen such things before. I have seen this thing also before. I have seen this thing before. But we have to maintain edges as pairs, and then we have to direct them. That is being a bit tedious for me. How do we direct edges? What is a nice way to direct an edge? I mean, how do we store that is what I'm just trying to think. Because after solving, we have to make it a bit better, right? Always. I may appear small, guys, but I have nice muscles. They're not visible though. See, tricep. Even biceps are not visible somehow. I can do this too. So if I start OnlyFans, so it's dropping eight viewers. So I will try to implement this problem. I'm only thinking one thing: how can I direct them well? Like how do I maintain? Should I maintain for each edge zero or one? And who will be the parent, the main parent? Anything can be the main parent, but yeah. So we have one component, right? I will take one vertex, and then for all the vertices, okay, if this vertex has zero, means I will find parent. For all the one components, I will find a parent. So I think let's simplify the implementation. So once you find a one component using some vertex v, let's try to find, do DFS with that, and then keep its parent. We will find its parent, and we will, if this is one, then we will keep 1. If this is upward, we will keep 1. If this is downward, we'll keep this 0. Okay, so if we have parent and if we have this 0 or 1 value, then we can know if this edge is 0 or 1. And what should we do finally? What should we finally do? Once we know all the directed edges, once we know the direction, what should we do? So direction of all ones will be fixed. And for zeros, let's come to them finally. For zero vertices, what do? We will direct everything outward, and then we will find that 1 1. Oh, we can direct everything inward for zeros, and then we will find that 1 1, and then we will only flip that one. So zeros, all the zero vertices also will be taken care of. Okay, zero vertices will be taken care in this way, one vertices will be taken care in that way. And then how do we maintain these edges? Should I just try to store in this adjacency? Should I try to push this to show the direction? And then how do I solve the problem? Like we have something that has everything outgoing. If everything is outgoing, so if something is having everything is outgoing, let's say okay, let's just put everything outgoing. If this is an edge, let's put this value in this one. In that way, we have our edges. We have our edges. So we will have these directed edges now. And once you have those directed edges, we will try to find something called in degree for each vertex, like number of things that are coming inside. Okay. And we will be focused on in degree 0. We will remove that and then we will adjust in degree of every other things. And then we can do that. So if we can just find these edges, outgoing edges, and then keep this in this, then we are good. Outgoing. If so, what do I mean? Once you direct this, if you can just add this to this outgoing thing, then we are done. So the whole implementation is clear now. We will find a vertex. We will find for everything in this subtree parent, and we will have 0 or 1. If it is 0, means it is coming like this. If it is 1, it is going like this. This based on this or this, we will add this to this or add this to this. For zeros, we will add them in separate way. And finally, we will have in degree for each thing. And then if in degree is 0, we will remove that. And then we'll proceed further. If there is a 1 component, it's impossible. If there is a 0 component, if there is a failing 0, it's impossible. So the whole implementation is clear, right? You guys can't understand all this or what? You guys should push yourself, okay? So the implementation is clear. To me at least. Fuck. Now see how a pro implements. I should be doing work. Why parent? To handle black edges. Okay. We need parent, we need direction, let's say. Dir of V indicates direction of V comma parent of V. The above things are only for black vertices. We'll also have visited. This out will be used finally, okay? These are values. We don't care about the value. We only care about the parity. Right. So now what do we do? We will go over all. Let's say we'll first do the first test. Zero vertex test. If a zero is surrounded by all zeros, then we are fucked. So let's keep it zero. Zero one is like if there is a one for a zero. Okay. So there is some one from zero to one. So if there is nothing means a zero is surrounded by all zeros. You can never remove that zero. So answer is no, and we can end the problem here. So why am I storing these vertexes? We will use it later, right? We are trying to think of directing them in this way, right? We're trying to think of directing them only them like that. That's why we can direct them right now itself. We can break here too. We can direct them now itself. But it will be too complex, or it may not be complex. Let's just direct them now itself. Out of, not out, yeah, out of. So what does this mean? We are directing V to U, right? So I will find our I will put our direct edges in this out array, because as outgoing edges we'll put them in, and then we will find the in degree, and then we'll keep removing in degree zero ones. Okay, that's the ordering. In degree zero ones we keep removing. You guys should have seen how I proved this. If in degree is not zero, you can go behind, you can go behind, you can go behind, and you cannot go indefinitely, right? After n, you don't have enough vertices to go indefinitely. You will never come to something that is already there, because that makes a cycle. So you will end up with something that is having everything out, and you can choose that as first. That causes no problem. Okay, now one components. If a of v equals to 1, continue. If a of v equals to 0, continue. Now do DFS. Okay. What do we do DFS? That's it for today, guys. I'll sleep after this. We don't want to repeat components, right? So we have to keep a visitor array. We want its size too. See, we can use size, or we can go and check for the parent, if parent is satisfied or not. So let's not use size. Let's just check the parent, if parent is satisfied or not. Then we don't even need these things. Maybe we need those things. We don't even need these things. We don't even need these things. We can just check the parent. So what do we do? What does DFS do? It will direct all the edges in the subtree. That's the definition, okay? All the edges in this has been directed. Now, all of them have been directed. So now you can decide for V. Should it be above or below based on its size? If its size is odd, you have to add the parent. If its size is even, you should not add the parent and you have to add this to the parent. Because it's a tree, I will also keep the P. We don't even need visited in this case. Oh, we need visited to not do repetitions, right? We only visit black vertices, okay? So what does DFS do? It will fix all the children. Now we are at V. We are thinking V and P. Should I add P to V or not? If out of V dot size reminder 2, if this is odd, our goal is to have everything even, right? If this is odd, then we have to add parent to this. I mean, if V equals to P, we cannot do anything. If V not equals to P, V equals to P happens only for the root, okay? Now we have to add V to the P because we have to direct it opposite direction and then we'll return. So now we will check here. We don't even need size. So now we have done for all the vertices, all the zero vertices, all the edges that are connected to 0 and 1 has been done. All the vertices that are connected to, oh, we are left with 0 comma 0 vertices. Uh, we have to deal with 0 comma 0 edges. I don't think you guys can follow this. You have to wait 5 minutes to comment. So guys, I'm trying to direct all the edges. All 1 1 edges has been directed. But 0 1 edges, we are thinking a bit. 0 0 edges, we are thinking. I mean, leave 0 0 edges. It doesn't matter, right? You need not direct everything. But 1 zeros, you have to be careful. Okay, you have to be careful that for all the 1 zeros, so I think 0 0 you need not add an edge at all because 0 0 whatever it comes it doesn't matter, but you have to make sure that for all other 1 0 you direct them correctly. That's all you have to make sure, okay? So let's do that again. Okay, there is one specific thing. Okay, there is one specific thing. For this, what we do is, for this we make v to u. For other things we make u to v. And for 0 0 edges, we need not add an edge because whatever comes first, it doesn't matter. So this is enough. This is good enough. We have directed all the edges. We are not directing 0 0 because it doesn't matter at all. Now, let me have something called in degree. Okay, problem is done. So we are having in degree for everything. Okay. Now whatever has in degree equals to 0, we put them in a set. See, we have actually know that if the component size is odd, then it's impossible. Even if it's odd, it's impossible. But we are not using that anyway. If the component size is even, it's impossible. But we are not using that. It is indirectly, this check will indirectly check that. If in degree of v equals to 0, s dot insert of v. We are taking a 0 vertex, we are removing it, we are pushing it to order. In of u minus minus, if in of u equals to 0, we add u to s. It's an easy problem. I have overcomplicated it a bit. Zeros doesn't matter, but then I tried complicating it a bit. So we have no s. Oh, we have many no's. That's wrong. Everything should be yes, but we have this no. We'll try to debug that. It's third test case, right? Why do we have a no? Why? Oh, it says this is failing. But how can that fail? 1, 2, 2, 3. I'll draw the graph. 1, 2, 2, 3, 2, 4. 3, 5, 4, 6. If I have a drawing pad, I can show my beautiful handwriting to you people, okay? And what are the values? 1 is having 1, 2 is having 0, 3 is having 1, 4 is having 1, 5 is having 1, 6 is having 0. So look at odd components. Oh, this is failing. According to my logic, this is failing. Did I do something wrong? Did I not read the problem? Oh, it is right. No, no. Answer is no. Why did I confuse? Oh, received output is wrong. How the fuck is received output wrong? Here it gives no, but why is it not giving no here? Am I not clearing something? Oh, visited should be made zero. My solution is right, but I haven't made visited zero, I guess. Now it's giving no s no. But why is it not outputting everything? So let's investigate this case two a bit. It's almost done, guys. People that wanna leave, it's almost done. This should not be happening. Unless there are cycles, this should not be happening. But there are no cycles, I believe. One, two, two, three, three, four, right? One, two, two, three, three, four. Values are 1001. Okay, and we're outputting 2 and 3, but not 1 and 4. Why? After removing 2 and 3, you can remove 1 and 4, right? Why are we not removing it? So for this 0, we pointed it like this. For this 3, we have pointed it like this. Oh, this should be out, not adjoint. Damn, that is something scary. I think I should quit from CP if I'm making such mistakes. I should retire. So it's done, guys. Will it get accepted? Is there anyone watching my struggle? It's an easy problem. I overcomplicated it a bit, but I'm ending it after. The fuck is wrong answer on test 2? It is right. It is entirely solved. It cannot be wrong. It is entirely solved. I mean, it is entirely solved. For sure, it's entirely solved. There is no mistake in this, except if I am not being cautious. A of u equals to 1. I have to be careful. Like, I cannot keep my mind somewhere and think that I have the ability to solve problems when I cannot be careful, when I cannot be cautious. Still wrong answer. Let's not add this shit right now. Let's not add them right now because that affects our out degrees, right? Let's not add them now. Let's add them later. I thought it might cause some problem. We have to add them later. We have 0, 1 already. We have to add them later. That's it. Because they will mess up the above things, right? If you involve zero first. I don't think there is any other error. Even if I'm half present, I don't think I'll make another error. Mhm. Wow, wow. So for one thing, we are putting it like that, B to U. For everything else, it's inward. It is correct. What is going wrong in this? It is correct. Should I say the test case? What is happening, guys? I'm not having any GF. I'm free. How to check some text? What happened to my internet? Oh, it's virtual. That's why I cannot see the test too. My bad. We cannot see test two. But how do we solve? What has gone wrong? This is true. If something has that, that's true. That's wrong. With respect to ones, one should have even size outward. And DFS will do that. How will DFS do that? After doing its subtree, it will try to do it with its parent. Do you guys see some error? It's a simple solution, right? Is there any error? We are directing edges again here. Like if for only one vertex, it will go from V to U, and for everything else, it will come from U to V. So 0 to 1. You can remove that 0, and then that 1 will be removed. We are not touching any edges twice. All one to one edges will be done here in the DFS. All 0 to 1 edges will be done here. So there are no 1 to 0 edges. We are not touching them again. All 0 0 edges, we need not care about them because the order doesn't matter there. Hey, why haven't I removed this one? This should be removed, right? See, as I'm getting old, I cannot even see such small things. Like I made a submission to remove that and place that later, but I haven't removed that. It seems it is accepted. Like there is no error in this. Yeah, it's accepted. Uh, should we try some other problem then? Should I just sleep? Most of you guys are guess. That's why I'm worried to meet you people. Like the video. Now I'll sleep. I'm just joking, guys. You guys are great. I'm just joking. I just joked. Like, don't get disappointed like that. I will try to do meetup in internship week. Then I think most people will be here, right? Not internship week, but internship month. Uh, I think in March or April, people will come here, right? Are you mad, Piyush? I'm sorry. How to not do questions like you? I'm in Bangalore near Church Street. I'll try to move somewhere else, but should I try G? I think I've overcomplicated this. I don't want to do G, but it is an interactive problem and I like interactive problems. So I'll try to do G2, okay? I'm hungry. It should be bad. It's not that difficult. But this hasn't been done by many, but it's not that difficult. It's not that difficult. I can judge the difficulty, right? So if G also should not be that difficult then. Let's go for G. This is an interactive problem. Interactive problem. You're given an acyclic. You're given an acyclic connected undirected graph. Why do you want to say it like that? It's a tree. It's just a tree. We define a path between two vertices as a sequence of distinct vertices, such that starting from here going there. See, they are giving you all definitions because you don't need any external knowledge. You don't need DSS, shitty DSS sheets. Okay, that's why they give all the definitions here itself. These are purely logical problems. For all I see, what have we used before? We haven't used anything. We have used only parity related things. We have only used that we can direct things. The ordering is nothing but directing edges, and the problem is for everything you should satisfy that the remaining things zeros doesn't matter, 0 1 doesn't matter, uh, Finding some necessary and sufficient conditions is all it is. Okay, it doesn't have topics. You have seen necessary conditions and sufficient. This is one necessary and sufficient condition. That is one necessary condition, and this is one necessary condition, and together they are necessary and sufficient conditions. And then we have output of the answer. Simple solution, like, okay. I don't think if it's a good thing to do to watch my classes, but yeah, if it's getting me some watch time, that's all I care about. I will read the problem. I'll just read this problem for some time. There are hidden vertices x and y. They may coincide. You can try. You can make the following queries. What the fuck does this mean? There are hidden vertices x and y. Okay, there are two x and y we don't know. They may be equal to. You can make the following queries. Choose two vertices a and b. The jury will respond with one if the path between the vertices x and y and the path between the vertices a and b share at least one common vertex, and will respond with zero otherwise. Oh, okay. We have a path. Okay, the path can be a single vertex too. We can query like this, and then we can ask that. Your task is to find at least one vertex on the path between x and y, no more than. So seems a nice problem. In no more than half seal, I guess. Not even seal, but floor plus one. The interactor is not adaptive. Think, guys, this is a nice problem. With the zero and ones, you have to find at least one vertex on this path. How do you do that? I think if you can make a equals to b, and then if that is on that path, then you found that vertex, right? So I think in that way you can find the vertex. If you do a equals to b, can you always shorten your path somehow? Maybe you can do binary search, but binary search may not work, will it? Let's say that binary search should work. Let's say that this is your path a and b, and you have found something in between x and y. There is something on this thing. Okay, you can choose mid, and then you can see if this is there or this is there. Tree will be given to us, right? A tree is given to us, so you can do binary search and find this vertex that is matching. And you can reduce, and then you will finally have that something getting connected thing. But how do you find first pair? Can you find first pair quicker? How do you find first pair? What if you just do edges? But edges will be like recurring, right? I'm trying to see, can you split the things into like that, and then you can do that. I figured it out, I figured it out from black and white. I think there is a way. We need not even do binary search. What you can do is, uh, see, if you can make the tree into two vertices, you can check if these two vertices coincide. if these two vertices coincide. And the first time you find these two vertices coincide, you will try this or this. Ah, that doesn't work. Oh, okay, okay. You can ask for this and then you will know the answer. So that works. That does work. Because x equals to y can be some vertex and still you should be able to find it. So I think, let's say initially all vertices are active. Okay. Let's say initially all vertices are active. You will try to take one inactive vertex, one active vertex and other active vertex, and you will ask for these two things together. Okay. If any of them is one, you're good. Else you will make them inactive. Now you should find another 1 comma 1 pair that only goes through active vertices. Do you get what I mean? You want another 1 comma 1 that only goes through active things so that you can check this path, and you know that once you check this path you know that uh, all the zeros will not have anything, you know that already, and if one of them has that then you can again check. So the problem is done, the problem is done. The only thing that's left is how do you implement this, how do you quickly get one and the nearest inactive vertex, nearest active vertex. Do you guys see how simple problems can be? No, the thing is it's like active and inactive. Okay, you have to choose a path that goes from some one to another one. In between that thing should be zero. Maybe root to leaves work, but root to leaves would not work, will not work. See, you will try to pair them. You will try to pair them, okay? From one to something like that. You have to pair them. Because if one vertex has many leaves, okay, if one vertex has many leaves, initially you can pair these two things, but then you have to pair these two things. You have to pair these two things. So you have to find the nearest, you have to find the nearest one. Can we do this recursively? Can we do this pairing recursively? Maybe we can do the pairing recursively. Okay. If you can do the pairing recursively, then let's say you have paid all these things, you have paid all these things, you have paid all these things, you have paid all these things. Okay. And if something is left out, one vertex can be left out because after pairing all these things, one vertex may be left out, right? Because if the size is odd, one will be left out. So one will be left out, one might be left out. Now what do we do is, because this is also there, we will take something here and first we will do these two things. Okay. So now both of them will become zero. Now what we will do is, now we will pair these things, and then one may be left out. If nothing is here, this one itself will be left out. If at least one is there, first we will pair these things and then we'll pair remaining things. In that way, we can recursively leave one vertex out here and we can query everything. We are done. The problem is done. The first time we find something is active, we know the pair, right? We know the pair. And once we know the pair, see, guys, problems can be done very quickly, very easily. Like if you try optimistically, I have seen n by 2 plus half. N by 2 plus half gives out that you have to just pair them up. I'll call it remaining vertex. Okay. See, V is left, right? V is left, and what all are left? All these are left, right? First, we must pair V and that. First, we have to pair V and that. Okay. So how do we pair? First, we have to question. This will actually protect it. Okay. Previous thing doesn't protect it. Because maybe you will leave here and then you will leave here and then you will maybe you will come here multiple times. Maybe you will come there multiple times. How can you come there multiple times? You left that, you assign done, but then again you are coming here, let's say. Let me check for this thing. 1 2 1 3 1 4 1 5 1 6. It's asking for 1 2, right? Let 5 be the vertex, okay? Fuck. Guys, what can be the mistake here? I think it's correct, right? What can be going wrong? Why is it idleness limit? Wait, wait. There is no guarantee that we will find a pair. And if we were not able to find a pair, then the answer might be the remaining one. Let's test this test case. One, uh, one. Let's keep it five. One, two, three, four will get paired. Five will be left out. Okay. One, two is zero. One, three is zero. Three, four is zero. Oh, this is wrong. But if we compile it and then if we run one, two, one, three, 1, 4, 1, 5, 0, 0, it found it is 5. Buzz by American flag, through the cherry to the light. Good night, guys. I'm sleeping. I have done two problems. You will say that to me if I only solve the problem and not when I'm struggling here. Both are easy problems. First one I overcomplicated, second one came too directly. Good night, guys.